So, I'm still Dead Program. This is still GopherBot. We're still at La Pipa, and now, hopefully, this is not Pantomime, which is going to be my new video with no audio service. It's kind of like Clubhouse, but it's the reverse. Yeah, so if you want to fund that, let me know through sending a video with no audio indicating the size of the check that you want to write. Okay, so news of the world, or off the world. So I saw this earlier, and I just could not resist. So unfortunately, everybody has technical problems, both on this planet and off it. So this is from earlier today, where the Russian Nauka module was intended to dock with the International Space Station, and here's what happened. So the thrusters fired inadvertently and unexpectedly, pulling the entire space station about 45 degrees out of attitude. Acknowledged a situation. So they used a different space module docked at a different port on the space station to move it back into its position. They got it back. Flight control team works through procedures. So if you've ever felt from taking down the production database, or accidentally restarting a server that shouldn't have been restarted, if you ever felt bad about what was going on, I direct you to our dear esteemed colleagues at NASA and also the Russian space program, where everybody was obviously very, very nervous that they were going to accidentally take down the entire International Space Station. And when we say take down, we mean down. Wow. Okay. So if you were having a tough week, just put it in perspective. All right. So other interesting things, Playdate. So if you haven't heard about Playdate, Playdate is a gaming system which is built on open source hardware and software, although I don't think it's fully open. But they finally have taken pre-orders. So this is an image of the Playdate. And the thing that's so interesting about it is this crank. Yes, there is a crank on the side of the Playdate whose purpose is to make it so you can crank it around during games that are specifically oriented towards doing this. So when we first saw the Playdate, a lot of us were wondering, is this a joke or is this real? Well, it is real, and apparently in the first 10 minutes they pre-sold about 250,000 of them. So looks very interesting. And furthermore, the Playdate SDK, which is not out yet, they say it will include Lua and C APIs. So will we see TinyGo on the Playdate? Well, we are hoping. We'll find out. So Go 1.17 is not out yet, but it will be out very soon. The first release candidate is out, and there have been a number of changes which actually do impact TinyGo. So as usual, we're working on our next release in order to maintain compatibility with the released version of Go. Sometime next month in August is when we plan our next release, and we expect that we should have everything working wonderfully, thanks to our amazing community. And then this last week was the first TinyGo mini-conf. So organized by the Go Developer Network. Amazing job from our colleagues over there. Also amazing presentations from many people well, 3 other people in the Go hardware hacking community. So you can check this out online. We have it all available for you. They were editing down the individual videos, but right now the main video with the full 2 hours and 45 minutes of amazing content is all available for you. So it's really, really cool stuff. And please do check it out. All right. So this week I was really, really busy, and I did not have a chance to review some of the amazing pull requests and work that has been going on with contributions. But one of them that I actually worked on myself is adding the search capability to the TinyGo website. So Tobias Steele, who is one of our contributors and the author of the TinyGo book that's on Pact Publishing, go check it out. It's a really, really cool book. I have a copy myself. So he was suggesting, wouldn't it be great if we had site search? And I thought, yeah, actually, that really would be great. So I added this pull request to the TinyGo website. And if we take a quick look, let's see if we can get it to actually work here. Yes, here we go. So because it's built all on Yugo, we can pretty easily make changes. And so this is the new site search capability that's just running in my local mode. So if I type in, for example, Arduino, you'll see that here's some articles that are popping up with Arduino, for example, the Arduino Nano. So let's click on that. And it takes us to the real website, because all of the site pages are actually indexed through this really cool service, which is called Algolia. So Algolia is really specialized in creating search for documentation websites. So we tried the Google site search, but it was a little, how do we say, advertising full in our particular context. So we tried this Algolia search, and actually it's really, really cool. So I don't know if anyone has a chance to check this out, take a look, but I would love to merge this pull request from me to the TinyGo website. So hopefully people get a chance to check that out, give it a try, and we'll get it merged in. Okay, so in the world of other TinyGo pull requests, there are so many amazing contributions that have been coming in for the last couple of weeks that we're actually quite behind. Actually, longer than that. We have some pull requests that are actually all the way back from last month. So if you're waiting for it to be reviewed and we haven't done so yet, we're really sorry about that. We'll try to be a little quicker at getting some feedback to some of you who are waiting for that. For example, this really cool pull request from Oliver Fuchon. So this actually adds support for the Blackmagic debugger, which if you haven't seen the Blackmagic debugger, it's a pretty interesting hardware-based. Let's see if there's a picture of it somewhere in here. I'll just Google it. Blackmagic debugger. So this Blackmagic debugger is a really cool. Oh, actually, there's a good one. Picture of the probe. So it's an open source JTAG and SWD debugger. So you can use it for flashing boards. You can use it for connecting to boards using GDB, the new debugger. So, and it's all open source hardware and software. So this pull request adds support, and I don't actually have one of these to test. So I would like to try it out, but hopefully we'll get that reviewed and we'll get that in there. So on the subject of the Raspberry Pi, so the RP2040, which is the awesome new Raspberry Pi microcontroller, we have several pull requests that have been added. If you may recall, last release we added quite a bit to the support for it, including UART support. We've got ADC, analog to digital converter support, and of course GPIO. So there's some pull requests here from Pipatv, who has been contributing a bunch of interesting things in documentation. So this pull request was actually started, when was it started? 21 days ago. Wow, that was a long time in the world of TinyGo. And so this is actually adding the SPI, the serial peripheral interface implementation. So I thought, let's take a look and see if we can maybe get this merged in today. So let's take a look, first of all, take a look at the files that were changed. We see adding to the list of different definitions for pin types. So this adds to that enumeration, so very good. That seems legitimate. Then this function here, which configures the pin to use the preset functions that are part of the PIO interface. So the Raspberry Pi RP2040 actually has sort of like 2 cores on a single chip, one of which is a more traditional microcontroller, and the other one of which is a programmable hardware interface that can be used for a whole bunch of different purposes. Traditional type of microcontroller interfaces like SPI or I2C, UART, but also some other interesting high-speed type applications. So that's what's adding that. And then let's see, adding to the machine package, which is part of TinyGo, the hardware abstraction layer. So we see that Pipatv has added the same basic interface that we normally see when we're using the SPI interface on other platforms. So I really see a couple of things that probably should be changed. For example, these errors here are not actually exported. They would need to be capitalized in order for them to be exported. So let's mention that. This should be capitalized in order for it to be exported for callers to use. So if that error actually occurred when you called this code from your own code, then you wouldn't be able to retrieve the error. So that's no good. So we got to do that, basically. And same here. Same as above. This right here would need to be also exported. In Go, the default is that when something's capitalized, it's exported, not the default, the behavior. And if something's lowercase, then it is not exported. So that would not be very good. We definitely want to do that. So here is the type, which is the SPI struct, pointing to the Raspberry Pi's own wrapper, or registers. So that looks in that block. So that looks good. And let's take a look here. Here's the TX function, which is the same transfer and receive function. The SPI hardware interface both sends a byte and receives a byte at the same time. If all you want to do is send, you can just throw away the one that's received. And if all you want to do is receive, you can just send a 0. So that's why this TX function here has both a slice to be written and also to be read. So in the logic, this is where it's pretty similar implementation to what we see in a lot of other TinyGo supported hardware, that it's looking to see if there's nothing to be written, then it only reads. If there's nothing to be read, then it only writes. And only in the case where it actually needs to do both does it read and write. So, okay, looks good. Here's the transfer function, which is what actually reads and writes a single byte from the block's own register. And then setting the baud rate, similar to the UART, the serial peripheral interface has a baud rate. Usually it's set pretty high because most of the devices are pretty fast. So we set and get it. And then our configuration function, which takes the SPI config structure and then lets us use that. So if we want to set different default parameters, so that all looks pretty good, pretty much as you would expect. Then setting the internal Raspberry Pi's PIO functions to the SPI interface for all of the different pins, so that's correct. Okay, so what's all this here? Verified this code below. So this looks like, it looks like there's some settings about turning on the pull up or pull down resistor that is connected to the clock. And I'm not sure what this is supposed to do in the context of the Raspberry Pi RP2040's implementation of SPI. This is commented out, so it's just going to do nothing right now. And I guess we should say, should this be removed? Be removed? Or is it needed? So I don't know the answer. I mean, we're going to test this in a minute so we can try to figure that out. But hopefully the author has some idea. And then this is the init SPI function that actually does the work. So that's setting the necessary. So this would be where things would fail because of this not being exported, right? So if you call the configuration function and you care about that error, and the error that's returned by init SPI, since it's not exported, well, something's going to go wrong there for sure. And then I guess probably you'll get an error back, but you won't be able to compare it to these types. So if you wanted to say, if air is equal to air SPI baud, then you wouldn't be able to do that. You'd have to look at the text, the string of the description, as opposed to just comparing the error directly. So it would definitely be better if that was made an exported type. So let's see what else we got here. Set format. That is the SPI format that's used for what the mode is, basically. So that's handled in this function. Looks like it's probably okay. Since data bits and mode are both by default unsigned 8-bit integers, and because the register in the SPI bus on the Raspberry Pi 2040 obviously is a 32-bit unsigned register, we need to convert this here when we're bit shifting it over. So yeah, that seems like it's probably okay. Then I'm not sure why these are set to inline, if that's actually strictly necessary. These are some functions that are not exported in order to do the reset and to uninitialize. Let's see, when do we call those? Probably in the config function, I would think. Or maybe init SPI? Let's see. Do we ever call that? That's a very good question. Let's see if that function ever is actually called. Reset, open paren. Okay, yeah, so that's the first thing called in init SPI, so that's needed. And then dinit. Let's see if that's ever called. Oh, gosh, yes. Have to have some water here. All right. So is dinit ever called? Dinit is called as part of reset. So I guess it's okay to have this layered. First, reset calls dinit, and then the config calls reset. It might be better to put this all into a single function, since it doesn't look like dinit is ever called separately. But that's not such a big deal. It's probably not worth, worrying about. So then, is writable. What does that do? Whoop. Is writable. Let's see where that gets called, if anywhere. Okay, so if writable, that's the function here that's checking to see if the SPI um, register is available for us to put some data into it. And if it's not, then it just waits forever here. This might be a good place for a timeout in the future. So let's mention that. This would be a good place for a timeout if the port is not writable after a predefined period of time. Just because otherwise what would happen here is if the port is never writable, then this loop will never exit and it'll just be stuck there locked up forever. And that's probably not good. I guess same thing with is readable. Is readable. Same deal. In the same fashion that we definitely don't want to, let's go back to, this would be another place. Same as above. We do not want to get locked in if it never is readable. Oh, readable? No, readable. There we go. Okay, so that's good. That way we're probably doing the right thing. Let's see. Let's keep going. Taking a look at, so print reg. This is like a debug function. So okay, that's probably a good thing to have. Actually, that wouldn't be a bad thing to have just generally in a lot of these machine implementations. Just when you're trying to figure out the inevitable question, why is it not working? So is busy is no doubt going to be the same as needing a timeout. Yeah. Let's mention that here. Timeout. Let's see. Timeout would be helpful here. So yeah, that's. And let's see if there's anything else that seems. Here we go. So this is interesting because this function here, which does both a transmit and a receive, it actually has, no, it's not using an actual timeout. This is just mentioning the fact that when you call this function, that it's not really guaranteed to exit, I would say, if it gets locked into one of these loops with is it writable or not. Let's see. Because if it doesn't actually perform the write, if it's never writable, let's see, then it'll just keep repeating over and over because it will never actually transmit or receive anything. So this is another case of where the loop could use a timeout. A timeout would also be good here. So yeah, lots of needs for timeouts here. Well, now that we've criticized all of these different implementation details, let's actually give it a try and see what happens. So for that, we can, let's go over to, this was my website test before. So let's say site. So let's go back to the main TinyGo repo, and I'll use GVM, the Go version manager, to use Go 1.163, which I know I have installed and is currently working. Actually, let's see what versions I have installed. Yeah, 1.16.3 is the most recent I have installed at the moment. So that's okay. So let's go over to the TinyGo repo, which I keep in my development drive. And then inside that is the repository with the actual TinyGo code itself. So git pull rebase origin dev to get the development branch all up to date with whatever's in there. Let's see what was merged since the last. I think I need to actually git fetch to pull in the tags so I can see, yes, the 0.19.0 tag, which was the most recent release. So now if I run TIG, we can see that this was the most recent release back on the 24th of June. And we see that there's a number of commits that were merged in that time. Bunch of changes to the interp module, which this is a bunch of code that was added for fixing some issues with the WebAssembly support, in particular running in the WASI interface, so that's pretty cool. A couple of bug fixes, and this is also for WASI support, so looking good. We're up to date on that. So let's pull in the SoyPat Pico Spy branch. So we'll git checkout. Branch with this branch name, the SoyPat Patch Pico Spy branch, and it's going to be based on the current dev branch on my local machine. So then when I pull that in, I have to modify it so it doesn't add a merge commit. So I'll need to add -- rebase to this command. So git pull -- rebase, then the SoyPat fork of TinyGo, and then bringing that into the this branch. Okay, and so we can see now. Let's take a look and see. Here's the SoyPat commits for the. There's 3 of them. It looks like, and if we take a look at the actual, there's 3 commits in this pull request, so that should work. So let's build it. Probably didn't actually need to build the whole thing, but that's okay. While we're doing that, let's go and jump over to taking a look at the actual Raspberry Pi itself, which I have here. Actually, let's look on the micro camera because that's just so much cooler. So this is the Raspberry Pi RP2040. This is the actual board from Raspberry Pi itself, not one of the cool boards that came out subsequently, that from Adafruit and from Seed Studio. This is the actual original first board that I got a bunch of from the Raspberry Pi folks. Thank you very much. So I have connected to it my FTDI adapter, which is what lets me connect the UART. Since we don't have the USB serial USB CDC support quite yet, then I need to use this separate external adapter, and that way I can plug it into my computer and actually see some output to know, if it's working, if the code I'm testing doesn't necessarily have some way of showing me that. So let's go back to my build here, which is now finished. And so we need to just copy this into the right directory, which is copying the built version of TinyGo into actually the Go 1.163. Actually, I'm messing this up totally. The easier way to do this is just to actually do the copy from, let's see if I can find, bash, history has failed me. So let's see. If I say go env, then I will know that, in fact, it's the Go path. So if we look at this, I'm copying into this global bin TinyGo of my previous copy, right? And you'll see that that's, in fact, the same path as, if we go up and scroll a little bit, where's that? There we go, go path. So it's the go path. Oh, here we go, go path, right? Because that's taking our package sets, global, but then we add to that bin tinygo. So if instead of all this, if I say I want to copy it to the go path, taking advantage of this environmental variable that's already set for me, I think that will do it. Oh. Let's see. No, it says it was. Oh, I see. We have to copy it in just to the bin directory. Like that? No. All right. Something's not quite good there. It looks like I don't actually have that directory. Is that possible? Yeah, no, it's in there. Global bin. Yeah, that's where it would go. Okay, so if we just take all of this, and I only have this problem because I try to run so many different versions of Go at the same time for testing purposes, naturally. So if we copy into this directory, global bin tinygo. Okay, so now if I run tinygo version, I should see that it's the development version for the next release, which in fact it is, and the SHA 91B 3969 should be the last commit, which in fact it is, 91B 3969. So, okay, I have the right version of tinygo. Excellent. We're off to a good start. So now, if we go and we take a look at my, actually, I have to bring up the code for this in VS Code in this case. Yes, there's an update later, much later. So let's go and take a look at I have a sample application. One of the examples that's built into tinygo is to test a SPI device. Which one? It is the APA 102. Let me find it in here, which is one of the SPI LED controllers, often known as, not NeoPixels. NeoPixels is the older one. Let's see here if I can, where is this? I got all my stuff disorganized. There we go. Source, and then examples, and then, oh wait, it's actually not in this repo, it's actually in the tinygo drivers repo. No wonder I can't find it in here. So let's go over to the drivers repo. So BC to create a new tmux session, and I'll rename it drivers, and I'll use GVM use go 1.163. Then we'll change directory into development, tinygo drivers, and we're the latest release driver, so that should certainly work. Let's make sure we can still see the tinygo command, tinygo version, so we got the right version there, so that's good. All right, so now let's go and let's modify the example for the APA 102, which is in these examples here somewhere. We have so many of them. APA 102, here we go. So the APA 102 is this, I can show you it. It is a microcontroller inside of an RGB LED. So it's very small. Each one of these is actually its own little microcontroller. And the way we communicate with it is by using the serial peripheral interface, SPI. It doesn't send information, it only receives it. So we send commands to it, and then we can actually control the colors of each individual light here, right? So it's got 4 pins that we would need to connect: the ground, the power, then the clock in, and the data in. So when we take a look at the actual Raspberry Pi, we will need to figure out, of course, which pins are which. And since on the Raspberry Pi RP2040, that is the original one that came from Raspberry Pi, the organization, the pins are all silk screened on the other side of the motherboard. So let's look at the RP2040 and we'll take a look at this. The website that's started at allraspberrypi.org. And let's see if we can find the pins for it. Actually, it'd be easier if I just search for that because they have a lot of stuff on their site. Pins, pin out. There we go. All right, so here's a nice looking image of the Arduino Nano RP2040, which is the Arduino version. That's not the one we want. This is the one we want here, which is the one from Raspberry Pi itself. Let's see if we can visit just that one page. No, we're not seeing. I'm not seeing the pins. Let's go back. This looks like the same board, and it looks like it might be a little easier for us to go directly to that image. There we go. Okay, so this is the Raspberry Pi Pico. It's the same board that we have, and you can take a look and see actually from this that there are quite a few pins. The ones that we want are the SPI pins. So it's going to be, I will guess. Well, actually, let's not guess. Let's go back and see if maybe Soy Pat, what did he do? He did not mention the pins that he was using for his demo. So I guess we'll just make our best guess. So let's go back here, take a look. It's probably going to be, actually, let's go and look at the definition for the SPI interface, because maybe we need to be specific. So it's SPI 0, and SPI 0, we can actually define a number of different pins. So let's go figure out how we can specify that. Well, maybe he said the default. So to find that out, we can go and take a look at the actual pull request. And if we go take a look at the files changed, probably in the board. Oh, actually, it's in the board definition already, I will bet. If we go back to the board definitions in the main TinyGo repo, and we go into the targets, the machine, and we look at board RP2040. Let's see, it's in here somewhere. Might be Pico. No, let's see. Is that what do we call it here? I forgot myself. One way to find out is just go to the TinyGo website. Look at the documentation and look at our reference section for our list of microcontrollers. And we can see, this is where I need that search turned on, right? So let's do a search for on the page. Raspberry. It didn't come up. Well, let's see here. I think it's Pico. Yeah, it is Pico. That's the only one that's not named RP2040 something. All right, so we can go back to the code here and we can see that the Raspberry Pi's Pico, we did not specify in the board file anything other than the onboard LED. We didn't so let's go and see. Maybe those are the same pins for all of the boards in this category. So if we go and we look at the machine package for the RP2040, we can see that are there any default SPI pins? No, I don't think those pins are ever actually defined. Let's go look in this SPI definition. So yeah, the default SPI pins are never actually specified anywhere. Oh wait, here we go. This is, it'd be nice if this was actually documented in the board file. So we should maybe mention that. Let's go back to the pull request here. And let's say that it would be here. This information, this info should be in the board file for the Raspberry, for the RP2040. So it can be more easily found. Just because I knew to look through the code, but other people out in the real world probably would not have any idea. Oh, hey, my main man Elo is given a shout out, I think, from David, an awesome hardware hacker and a person who has even more cables than I do, actually. So let's see here. Back to the subject at hand. So the SPI 0, which is the one we're going to use, it uses GPIO 18 for the clock, GPIO 19 for the data out, and then GPIO 16 for data in. Okay, so let's go over to the pin out, because where is 16? So it's actually these ones here on the bottom, I guess, right. If we look at it, because clock we need is 18. 18 is also, so this is all on this side of the board. And so if we actually look at the board itself, we can see that it's not going to be too difficult because it's these pins right over here. So I should be able to take and just plug in directly my little LED strip. I just need to plug in the power, the ground, and then I have to have the clock, and then the, I guess it would be transmit pin GP19, because that's all we care about is sending from the Raspberry Pi to be received. And if we go back and look at this, we could see that would be SDO, right? So if we just use SPI 0 and we don't have to actually specify the pins in our code, but we have to use the right pins when we're going to plug in. So let's start with the clock, which is GP18, which is the fourth pin up from the bottom. So GP18 would be the clock. So if we look and we see that the clock in is yellow, so that's 4 up from the bottom. So 1, 2, 3, 4. That would be this one. And then the ground is the pin right below that. So that works out kind of nicely. So we can put that in, the ground right below it, right here. And then we just have 2 more to go. We need the power. So, of course, the power on this is not going to be quite as easy to get to because it's all the way up on the other side, not the other side, but the top of the board. And that would be the 5th pin from the top is the 3.3 volt out. So 5th from the top. So we take a look and we see that I actually am already using that for the, let's see, am I using it? 1, 2, 3, 4. Yeah, 5th from the top is plugged into, so luckily that one's already plugged in to our power bus here. So we can actually, instead of just plugging into the ground there, we can plug into the ground on our breadboard here. Makes it a little easier. And then same deal with the power. We can take the power and plug that in. Also, on the breadboard's power rail, which is this rail right here. So now we just have one more cable to plug in, which is the data in, which would be the transmit from our pin out diagram. So that was pin number GP19, which is the one that's right above where the clock is. So that should be pretty easy because we already have the clock plugged in. So if we just take this and carefully plug it into the pin right above it here. Got to get it in there correctly. I don't have very good cable. It's just sort of, I tinned the ends, which means put a little bit of solder on the ends of the wire. It's just that way it would plug in. So it's not super well connected, but it's probably enough for this test. Right? Okay, so far so good. So now we just need to actually flash it. So if we go over to our code in our terminal, all we should have to do, since we're in the driver's repo, we should be able to say tinygo, then flash. Our target would be the Pico. And what we want to flash is the examples APA 102 main. But before we do that, there is one thing we're going to have to do. And that is, if we go and we actually look at that code in our driver's repo, we see that the number of LEDs here is 30. And that, in fact, I don't have 30 LEDs on that strip. Right? I have, in fact, only 6. So we have to change the code, or else it's not going to work correctly, because the number of LEDs, the way that these APA 102s work is each one of them relays the signal onto the next one in this chain. So if we don't have the right number, we're sending signals to LEDs which don't exist, and it doesn't work very well. So we're going to have to go in and change that, just change that one number. So instead of 30, that we'll just change that to 6. And other than that, everything else should still continue to work. We're just using the default frequency, the default mode. On SPI 0, which we use the default pins, so that should all probably just work, right? If this excuse me, if this pull request is actually correct. We're going to find out right now. But real quick, we need to actually plug in to the Raspberry Pi, and in order to test this, we have to hold down the button when we plug it in, because the Raspberry Pi does not have, although it has the UF2 bootloader, the one that makes it very easy to flash, it does not have support for the automatic detection of that you're putting it into flash mode. I'm going to hold down the button when I plug it in, and it should hopefully come up in flashable mode. Okay, and yes, on my screen it just popped up a little notification that it sees the Raspberry Pi. So I should be able to flash it now, but no, because there is a problem with SPI 0 not being declared by package machine. Uh-oh, let's go take a look at that. So the Raspberry Pi, it should have SPI 0. Oh, we need to probably put it in the board definition for the Pico, because not all of the, well, actually all of the Raspberry Pi boards should have them. So let's look at the board, the main board definition in the machine package. Look, these are the UART pins that are the defaults. This is the same sort of predefined defaults that we would probably want. And, let's go and see, because I don't see how this actually can be called from the Pico. Maybe one of the other boards has it defined. let's go take a look and see if any of the other Raspberry Pi boards have any, because this is similar to the way the UART would be defined. Meaning, if we look at the board for the Pico, we should see, or the Nano, actually is another example. We could see for the Nano RP2040, we defined what are the SPI pins, what are the I2C pins, basically all the defaults. But the board Pico, which was the original one, we don't actually have those defined. If we go and we take a look, it's missing a bunch of those definitions. So that means we're going to have to add those in to even test this, right? We're going to have to go and we're going to have to say that these are the default SPI pins. And actually, this is not the right values for SPI 0. So that's another bug, right? That if it was going to use these normal defaults, if you expect that those are going to work, those aren't going to work, right? Because we saw from the actual SPI definition that when you use a particular bus, it's going to overwrite the configuration with what it thinks the defaults are. So if that's actually correct in the Raspberry Pi Nano, which is a really small one from Adafruit, let's actually go take a look at that. So the RP2040 Nano, and let's see, pinout. Sorry, this is the one from Arduino, not from Adafruit. That's the Feather. So the RP2040, if we go and we take a look at the pinout, we can see that the SPI pins, where are they on here? We see here's the analog pins, and here are, I can tell you that the reason why you're not seeing that SPI interface is because it has the built-in SPI connection for SPI 0 is being used to communicate with the Wi-Fi chip that's on board this device. So actually that's a bit of a problem, because since these pins are required to correctly communicate with that, and since we saw that the code in the pull request is going to overwrite those, then you'll never actually be able to use the Raspberry Pi Nano Connect's built-in SPI interface with the Wi-Fi chip. So that also has to get fixed. See how it's not easy to do this kind of coding, because you don't have all of the hardware to test it yourself. And so if you don't follow some very specific principles, you could run into troubles. So let's mention here, this will overwrite any values passed in by the programmer. Let's see, passed in by the programmer. This means that a board such as the RP2040 Nano Connect will not be able to use the onboard Wi-Fi NINA chip. So that's no good. So that will have to get corrected. That means a board, not the board. It'd be good to actually use the proper English language spelling, just because, theoretically I do know that language a little bit. Okay, so, wow, this is going to be a little harder to test than we thought, right? But that's okay, because so now in this case, we still need to define the SPI bus, and that's where this problem is occurring I'm not sure how SoyPat actually tested this. I'm wondering. Just because without that um, actually defined anywhere, I'm just wondering how, it would work. It seems like maybe there was some code that didn't get committed to the repo along with their tests, and that's a very likely type of scenario. That's very common, it's happened to me plenty of times. I didn't want to commit some test code thinking that it was going to make it, much harder for people when actually it was kind of necessary because otherwise you couldn't figure it out. All right, so let's go and let's put in that board file just for the sake of testing the overall pull request. So we go into the board Pico, and we can put in these SPI pin definitions, which are, as we saw before, actually should be clock is GPIO 18. The data out is GPIO 19. And then the data in is GPIO 16. Notice the Copilot, yes, I am running Copilot, and it's putting in the totally wrong info. So don't just trust your Copilot. If you're running GitHub Copilot and you think it's just going to do everything for you, I'm really sorry. It won't. No, it's just really good auto-completion, basically. Really, really good auto-completion, but that's all it is. All right, so back to trying to add the right bus in so we can actually test this. Let's see if the Nano defines that, which they don't. And I think the machine package for the UART is actually the closest to what we want. Because the, let's go find the actual definition for that. That would be in just the main, let me see here. Here we go. So we're going to have to define the, similar to where we define the UART, we have to define the SPI0 interface or else it's not going to be able to find it. And this really should go into the board, not into the machine, because this is specific to this particular board. So if we go in, this will make more sense in a minute when we finish it, right? So if we say that this is not the UART, this is the SPI, and this should be SPI0, and that would be, I guess, we probably don't have to do this extra work, but let's just do it anyway. So underscore SPI0 is a SPI that uses what? Let's go take a look at what we actually need to pass in for that configuration for it to work. It might be that the only thing we need is the, let's see. It looks like all the defaults might, default baud rate. So we would need the baud. So, but we don't actually need to pass that here. All we need to do is specify the bus. So the bus for this would be the RP SPI0. In other words, the machine package's implementation or interface calls the device package's implementation. All right, let's see if this compiles now, because I think this will work. No, we're still missing. Yes. That's because we need to specify here in this board package that it's using the right, if we go look at the machine package for RP 2040, we actually need to include the device /RP package for that to work. So let's go back to board Pico. So we have to import just this one. Okay, that should work now. Let's see. Okay, and guess what? It did work. Let's go take a look at the micro camera. So yeah, we can actually see it flashing. So we had to do a little bit of hacking on the pull request to get this fully set up. but most of it's really good. Wow, great job, Soy Pat. This is a big step forward because we just need to get a few of those changes in, and we can actually maybe use this. And we need it because there's all these cool SPI interfaces to cool devices like displays, analog to digital converters, all sorts of cool stuff. All right, so let's go back to our, I guess that would be 2. So let's name our tab in TMUX so we end up at the right place. So let's go and see what did we actually change. So in order to do this, I had to modify the Pico, and I guess we can just paste in this patch, and this will explain to Soy Pat what I had to do to get it to work. So if we go in here to the general comments, in order to get this to work, in order to test this on my RP2040 Pico board, I had to add the following code. Just that way they have a way to test this more directly. And this was added to which file? Ah, yes, board Pico. Okay. So let's just go and look at the preview to see that, yeah. So this is let's just explain what this is. The pin, or rather the SPI bus needs to be hooked up to a specific, let's see, the SPI interface needs to be hooked up to a specific bus. Or SPI 0 variable, maybe? We can just say SPI 0. SPI 0 needs to be hooked up to a specific bus for it to be able to be used. Really, that's the only, the pin definitions are just added for clarity. See my comments above. This way we can, like most of these boards will have the same pins, but, oh, looks like we have a spammer. Where's my mouse? Yeah, there we go. Let's see, how do I get rid of spammers? I know there's a way to do this. I guess it would be block. Ban. Goodbye. Okay. Nice. I like banning spammers. It's just something about it gives me a small pleasure. All right. Goodbye. Anyway, so the pin definitions are just for clarity. See my comments above. All right. This way, hopefully, Soy Pat can make a few changes. Oh, I should just say, by the way, the SPI interface worked on my Pico using an APA 102 LED strip. Good work, Soy Pat. Just because, you know, this person put in a bunch of time to get it to this point. So it's pretty close, right? If we just get these other changes made, then we'll actually be able to get this pull request merged. This is totally awesome. Okay, so that's just one pull request. So you can see it actually takes quite a lot of effort to to land code into a large complex project. And it takes a lot of effort to create that pull request in the way it can be. So there's a lot of collaboration that goes on with people who've never met each other in the real world, who are just willing to donate their time, attention, and kindness to each other. So, wow, this is totally awesome. All right, so there's also an I2C pull request from SoyPat. Let's just take a quick look at it, just to see like what's in here. So the let's see, looks like there's some code that may also sort of bump into some of these other pull requests that they submitted for the PWM support, which is also an outstanding pull request for the Raspberry Pi 2040, RP2040, so that's really cool. So that, let's see, what else we got in here? That's just cleaning up, setting a few triggers specific to the I2C interface, setting the necessary pull-up and function interfaces. Okay, so far so good. Here's the machine package with the code that was added. Same problem here is export. Please export. Please export errors here. Okay. I just saw that from before. So it's a very similar interface in the fact that the I2C interface is designed to both transmit and receive info. Differently from the SPI interface, it does not have the requirement of sending and receiving at the same, or the benefit of sending and receiving at the same time, but it makes it a lot easier to write code. You transmit some command and then you receive the response. So it's a little bit easier to work with. Similar fashion here of just overwriting the defaults. So let's just say, see my comments about this in the SPI pull request. See my comments about overriding pins, about overriding pins, just because if you think that you can set them by setting the configuration and it doesn't actually work, you probably wouldn't like that very much. Okay, so setting the baud rate, same sort of deal. And then enable. Is this, what is this? Why is this commented here? Let's see. Should this be removed? Looks like it was commented out, but was never taken out, even though it should have been, right? Okay, cool. Let's see what else we got in here. Probably some of the same issues as the other PR. I'm not going to go over through all of this right this second because I actually have a couple other things I wanted to work on today. But we can see that, does this have to do with, is this actually to do with this specific PR? Seems like something else. So it has the same, I guess the same concern that I had with the SPI pull request, which is that there's no definition for the actual pins. The I2C pins, or pin definitions are needed here, just like in the SPI pull request. Please. Also spelling would be good. All right, just that way. I'm sure that SoyPal will understand what I'm trying to communicate with that, just because I did specify it in the other PR. So, and then they actually submitted another pull request with the PWM implementation. So I'm not going to test this right now, but it's the same sort of deal. It looks like once the other pull requests are landed, it'll be a lot easier to get this all merged in and avoid any pull request conflicts. But wow, what an amazingly prolific period of time. Thank you so much, SoyPat. This is so awesome. If we could just get a few of these little tweaks made, we can get this thing merged. That would be tremendous. Wow. That is seriously awesome. Thank you so much. Okay, so I wanted to work on something else today a little bit. So if you saw my demo last week at the TinyGo Hardware MiniConf, you saw that I flew my Bluetooth-enabled drone using one of the controllers that I've made. And this particular controller, it's very homebrew, very, very homebrew, like way too homebrew, I think, maybe. So it's the NRF 52840 chip on the Adafruit Itsy Bitsy board. It's got my SSD 1306 display, some buttons, and then a single analog joystick. So the problem with this device is that it's on a breadboard, so it's not too difficult when traveling around with it for one of these cables to accidentally pull out, or for one of them to maybe go bad just because it's sort of jiggling around. Lots of things can happen that are, not very good, and naturally that cable will pull out right while I'm trying to fly the drone. I mean, that's just a given. Murphy's Law says that will happen. So there's another way to do this, which is actually, instead of just sticking in the cables into the breadboard, right, we could actually make a slightly more permanent board if, for example, we wanted to work with what's called a proto board. So a proto board is similar to the breadboard in that it's got all of the holes very well organized in rows and columns and labeled very cleanly. So I actually have two different sizes of proto board here, slightly larger and the slightly smaller. And one of the ways that you can work with this with proto boards is you can just stick the wires through the holes, which we can, as an example of that, let's see if we can just insert one of these wires that I just jammed into the breadboard before. You can see that that will fit into one of these holes. Hopefully you can sort of see that coming out the other side. And then we could solder it on, and then our wires are just directly soldered on. But, of course, that's quite a lot of work to solder on all these wires individually. And if we make a mistake or we want to change something, we have to desolder everything to try to put it all back together. So, naturally, if you make one small mistake, like you're off by one, then that's a lot of desoldering, and probably you could just throw the proto board away, because once it's all encrusted with solder, it's not that easy to get it off. You can use a special tool called a desoldering bulb, which I definitely use the desoldering bulb. It's like a little suction cup device that you, oh, here we go, look. Here's some solder now that I happened to solder sucker out at a previous time. So you heat up the solder, and then you push in the little plunger, and then once it gets hot, you push the button and it sucks the solder off of it with a little bit of vacuum. So, but it's not perfect. It can only do such a good job. So another way that you can do this is actually using a technique called wire wrapping. So I have here this really, really cool wire wrap job that was done Actually, it's just no. This doesn't use wire wrapping, does it? No, this is just really well organized. So I thought that. Actually, I forgot that this is not wire wrapped. It's just super well wrapped, super well organized. Just looks really nice. This was the work done by my friend Lorenzo, who is also a hardware hacker, who was on a bunch of the streams that we did earlier this year, learning to program TinyGo and hardware. So if I look at the little wire wrap tool and wire wrapping wire that he brought, we can see that it's designed to take this little bit of wire and spin it around so that it attaches to one of these pins. Let me show you what one of these pins actually look like. You can see that the way that this works is that this wire gets wrapped around with one of these pins using this tool, and if you solder this to the actual board, then it's a way for us to route these wires around on the board much more easily without having to solder everything on. If we make a mistake, we can just unwrap it and wrap it back, and it takes up a lot less space as well as being a lot cleaner. So I thought it would be really cool to maybe start working on replacing the flight control with another flight controller that's a little bit more permanent. And I was trying to decide if we should use one of these smaller proto boards, emphasizing making it really tiny, which you could see that it's maybe possible, right? We could probably fit the buttons on here. And then the other option is to do something like what Lorenzo did on that really cool interpretation of the project kit, right?
If you need, maybe I have...
So hey, Lorenzo's here right now.
Hello.
Hey, what's happening, man? How you doing?
I'm fine.
Welcome back from Italia.
Yes.
Land of the Arduino.
You're right. Actually, Messina, we have a development center. I mean, we had. I don't know.
I should put on my mask. That way we're not contaminating each other.
I have some boards if you need it.
So, yeah, I mean, I haven't fully thought this project through.
Okay.
You have, I think, those are very similar.
Yeah.
Pretty similar size board. We can take a look at here, actually, what you brought.
Okay.
Those are the small. I think that's actually where this board came from, as you gave me one of these previously.
Could be, yes.
This is even smaller.
These are two.
Oh, that's a double.
Yeah. And then we have these ones. I never came.
That's even big. So we don't actually have two sizes the same. We have many sizes here.
Exactly.
Many sizes. Well, when I showed you the controller here, Gopherbot, you'll have to supervise from a different position. So you can see here, there's not that many cables. There's the 4 buttons, each one of which has a ground and a pin.
Mm-hmm.
We have the 4 wires for the I2C display. We have 5 wires for the joystick, and then the power, which that's actually just coming from the USB that's plugged in. I didn't try to replace the power with something that was more portable. Just using a USB battery seems easiest. So I brought a few parts that I thought might be interesting to use for this. So for starters, I brought another Itsy Bitsy board. And I thought the Itsy Bitsy board would be really cool if instead of soldering it to the board, if maybe instead we could solder some pins and then use some headers so that we could attach and remove it if something goes wrong.
Something like that, maybe.
Yeah. Exactly. So,
I don't know if
pretty
that
much
one
exactly.
fits. No,
That one
it
doesn't fit, but exactly like this.
I have male and female, so in case you wanted to.
Let's take a close look at that, because that's pretty much exactly the idea, right? I mean, you've done this before. That's why I need your help, my friend. It's been a long time since I did a wire wrap, but yeah, having two, rows for the pins on the microcontroller to plug into. Obviously, this is not exactly the right size. It's very close, but not quite.
It works on the lily pad, I think.
Mm.
I don't have it here.
But that might be, I don't know if what's the right size, because I guess, do we want to try to make it as small as possible, or do we want to try to make it as easy to see how it's connected as possible?
Okay.
What do you think?
I don't know. I think for looking at the connection, if we can easily spot the wiring, and we can plug one of these, for example, into the board, and we solder just one pin. The ground usually is the one I solder, and then everything else it will be wire wrapped with some. I have another one which has some colors if we want to make some distinction in some cases.
Oh, you're saying don't even use the headers, just wire
I
wrap
just
directly.
solder one, because then if you want to pull it off, it's just the soldering one pin, and you don't have.
Oh, but that way you don't have to do the problem you have to do on this board, which is you have to jump over from the header to the pins you're going to attach the wire wrap to.
It's one option, yes.
That is a lot simpler, and it's also a lot cleaner because you can see where things are going.
Yeah.
And that for sure is smaller. Now, this might be too small, by the way. Since we have to connect. Now, let me show you what I was thinking of for the joystick.
We can have this is not, with 5, let's say, windings, this will be enough. 7 turns, and it keeps the board stick to the.
Well, with the joystick, I thought it'd be really cool if it maybe could just plug in.
Okay. Oh yes.
Instead of having the cable where it's dangling like this, where it's just so many things to come off.
Much better, yes.
That this would be a little bit easier. Not exactly this board necessarily, even though I thought the circular board was kind of cool, but it's a little too flimsy. This is part of my boards I got at Radio Shack, but while they still existed.
Okay.
The long lost Radio Shack. But anyway, I just thought this was kind of a cool, maybe not this many pins, but maybe a few extra, just so that way it has something more to anchor to. Because this is a lot easier.
You have a remote control.
Even though, like, the way that I'm doing this with a single joystick is you actually need 2 joysticks to fly a drone.
Yeah.
So when I push this button, it makes it so that this switches to the right joystick instead of the left joystick. The right joystick is usually used to go forward, back. The left joystick is usually used either to rotate or change altitude.
Okay.
So if I want to change altitude, I press the button down and then just tilt it up, and then I can let go of it and then just fly around normally at the new altitude. The reason why this is cool is it's really small in a single joystick and a single set of pins. The reason why it's not cool is it's much harder to fly.
Well, maybe one of those is.
So that's a good question: is do we really want a single joystick, or is it better to maybe
even solder it?
Have a double joystick? Where's my other joystick here? I brought a spare. Let's see, where is it? I have it. Oh, right here. It's just I thought this is going to be a lot easier. Plus, it looks more like a real thing.
Yeah.
Like that actually looks. If what we want to do is try to make it look like a more finished controller versus, the nice thing about the breadboard is it looks like you hacked it together, but that's also the drawback.
That's right. Look at that.
Yeah.
We might be able to solder it that way, and there is a perfect fit, so we don't mind if we solder that one.
No.
Then everything else could be, and I think.
But it's not going to be as durable Like the reason why I stuck the pins through is I get kind of excited.
Okay.
And so the only thing I would worry about is that, with this setup, that it could easily come off. It'll peel off because I get excited or drop it.
Okay.
Whereas, with it actually going through hole, I mean, this is a really bad solder job. Don't pay attention to that. But there was more just the concept of how it could be attached. And I did, where did I put the... I have a one that I tried experimenting with. Not this one. Let's see. I don't know what they did with it. Maybe I took the pieces off. I had, oh, no, this is it. No, this is not it. I have some longer pins.
What is that?
That this is from a ESP 8266. You know how it's got the long pins so you can stick it through the breadboard, have headers, and also the pins sticking out the other side enough to...
Perfect for wrapping.
Right. I thought, wow, that actually is pretty good. If we just bent the pins over... Let's see. It fit in this one. Oh, no, that's not the one. I had an actual board that I was trying this on. All these boards look all the same now, but before they looked like they were all different.
Yeah. Is this one, no? It does fit.
Right, but yeah, it's the same. That's the same type of longer. I did a really bad job of bending the pins, but I didn't actually use the proper tool. But you can see where that's actually really solid.
Yeah.
Like that would definitely stay on.
Doubling the soldering up below and on top.
Yeah, I mean, you maybe only need to solder one side. But the only thing about this is all the wires are going to be on the back side. And that makes it a little harder to put it down. And also it makes it a little harder to see. The design you did for this board, like, you have to do more work to connect the pins over to the headers, right? But this way you can actually see all of the wiring, and if you put it down, it doesn't have a chance of shorting out, or you could maybe put a little surface on it or something. I don't know. I haven't decided, just because, I've just been playing around with ideas of how to make a slightly more permanent, but still very hacker friendly. Obviously the next stage would be do a real board layout and make a PC board, but that's already too professional for what I'm trying to do here. But anyway, these were just some of the ideas I came up with. And I guess deciding, do we want to make a small as possible controller with a single joystick that's basically the same as this board, but smaller and more compact with less things to go wrong. Like, where's my display? Here's my display. The display fits on this direction, is it? Yeah. So it takes up a lot of room, on the board, unless we put it on the bottom. But then it's sticking off, so there's more things to get broken. Versus if we use a bigger board.
On top of or on one side you put the controller, and on the other. So you can reverse, for example, the controller in here and put the display on top. Maybe there is still some room. I know, because it makes... Well, here you put just one of these sockets so that you plug it off, and once it's ready...
This should be a little bit like this.
Yes, okay.
But we still need the buttons. So these buttons are really important because it's takeoff, landing. This one that switches between joysticks is not needed if we have two joysticks.
Okay.
Of course, if we have two joysticks, we have to use more wires, right? Because it uses two analog inputs, one for the X and one for the Y. But if we did it kind of like this, you could see where we have to have a way of putting it on so that the USB can be plugged into to reflash it, because the software will be changing continuously, as you already know with me. It won't be the same software 2 days in a row.
Well, this is the ideal one.
This is better. Yeah, this is way better.
You can break it, no problem. Or let me see if I have some. Okay, perfect.
I break it in the American way. I just break it with my hands.
Yeah, exactly.
I break it like I fix a Harley. I just kick it, and hopefully it starts to work again, kind of thing.
Yeah, that's much better.
Because I don't know if maybe it's better to put it on the side a little bit.
I would put the USB on the bottom and maybe the display a little bit up.
Assuming that you're going to need a couple rows of pins on that side for the joystick to plug in.
But the thing with this is probably still better to use sockets because you can get one of those damaged.
Yeah.
So it's easy replacing. It's a lot easier to replace it if something goes wrong.
Yeah.
Yeah, always.
Yeah, that's a good point. That way, if I need to pirate the parts, if I need to scavenge the parts to use for something else, which totally happens all the time. Like it's harder to get parts now.
Yeah,
for example, the SAM-D 51 boards, the ones that are used like in this, they're really hard to come by. Like they're supplied, like they're months and months behind. My friends over at Adafruit are making some boards using RISC-V processors because they can't get the ARM-based processors that they were using previously, and so they have a new board coming out with some RISC-V processor because that was the only thing they could get.
Okay.
Which is really wild, isn't it? Anyway, so I don't know how easy it will be to get another one of these soon. Anyway, this is a Nordic Semiconductor chip, so it might be a little easier to come by than the microchip AT SAMs, but I'm not sure. But I think you're right about the socket. That
Absolutely.
Seems like a better...
No. When you are prototyping, I think it's the best way.
Also, if we decide that it's the implementation is screwed up and we have to throw everything away but the processor?
Yes.
Yeah, good point.
I mean, even if you solder just one of those, but then redoing all the wrapping, etc., it's a pain. So, no. That's the... I think it was the way I was always working because of that.
Okay, so let's just say we're going to use the header. Whoops. Uh-oh. It's lost. It's gone. It's on the dark floor. You'll never see it again. So assuming, of course, that we take the idea you had, put it downward, but put it on a socket, it'll still fit in, but we need one more row of pins next to it to accommodate that, don't we? So it has to be at the closest, it needs to leave 2 extras on this side, or else you're not going to be able to do the, how will you wrap. This is where it'd be great if we had headers like this, but with way longer pins, like what I...
There are, but I don't have them, unfortunately.
I have none of those, I don't think. I have a lot of the same headers, but none of them are long. The only ones I have that were long were those ones that, like these, where I basically had some leftovers from the ESP8266, but there's only, 8 pins. So we need more. I think it's...
But if it's just for wrapping this, let me check. No, this is not enough. No, this doesn't...
Yeah, it's too
short. If we do
even this, I wonder if it's long enough.
No,
for you.
This is perfect.
This is perfect.
This is perfect. This is not. You need at least, I think, 3-4 millimeters.
So I guess the question is, how many of these longer ones do I have around that we can maybe borrow, meaning use forever? Let's see, I have 1, I have 2, which I think is enough for one side. Yeah, unfortunately, these are going to be really hard to cut.
No.
Well, you lose a pin.
Yes, you lose a pin. That's true.
That's else they don't perfectly fit because they're so close. So we have to like trim them.
I'll cut it, but then you have to sand it a little bit.
Yeah, yeah. But it's not the best setup compared to.
We need to be patient, maybe.
Maybe we need to actually get the right headers.
Yes. Or if we can go with wire wrapping this one as it is, and then change it. It's not a big problem anyway.
Well, the thing is that might be actually necessary because you're only talking about desoldering a single pin.
Yeah, yes, it's really.
So that's pretty simple comparatively. The only reason we would do that is something's gone terribly wrong with the board.
You don't even need to solder, not even one. I mean, it's once you wire wrap a few of them on both sides, the board doesn't move.
So let's just play with that idea, right? So that means it can actually go all the way up to just one pin. That saves a little bit of space, right? So that would be like this.
Yeah.
And then, let's see, where's the other? That was the one I did a terrible job soldering in, but at least you can sort of see the idea of how the two joysticks would work. And then we could put the buttons here, and that's actually pretty good.
Yes.
And what else is on there? Oh, the display. So, right here. So the display, we now almost, we actually really have just enough room to make that work, don't we? In fact, it could probably just go up here.
And with this, it's elevated and it
because the buttons then would go here.
Yeah.
So the display here,
much better.
And then these can be detached for transport and just plug them back in, and there's less. This whole thing can be wrapped up in.
Actually, if you do that kind of thing over here, you can bend it a little bit, which looks
that actually looks cool.
Ergonomic.
The only thing is, yeah, actually, I'm pretty sure that there's a programming setting that can reverse the display.
Well, I know I could do it, but
in the TinyGo driver for the SSD 1306, I'm pretty sure you can do that. And so, yeah, that would make it just that much cooler because that way the display comes off for transport, plugs back in, and has like a little tilt.
Yes.
Just to make it a little easier to.
Because the tendency I think it's to use it like that, the remote. Well, it's me, but what do you think? I usually have this.
Well, also it gives us the ability to use less room on the board, so we can actually see some room to put the buttons, versus putting it here, where the buttons are going to have to just be in a straight line. If we look at the buttons I have these very small little buttons, so they're colorful. And there are buttons built into the joystick. If you push it down, there's a little detente.
Yes.
But
it's too hard.
It's very flaky.
Ah, okay.
You push it down and you accidentally let go of it at exactly the wrong time.
I have some of these push buttons with LED colored ones.
But then you have to power it, don't you?
Yes.
And we have very little power. We need our power for the batteries.
Okay.
But these buttons are very small. And they're long enough for you to wrap them, I think.
Absolutely.
We could still spot solder them to hold them in, but that way we don't have to worry about like making a rail. Well, we still have to make a rail, right? Because the grounds all have to go together. How do you do that? Since there's just one ground pin on the chip.
Well, the ground is usually, I cannot see, but if I'm not wrong, I just do one with the same. Maybe I didn't not understand what you would like to do, but I usually use one of those and ground them all. For example, I decided some.
So you make a solder bridge just by
Yeah.
filling in all the pads with some solder, and that way
Yeah.
it acts like a rail.
Exactly.
That seems a lot easier. Do you
with
do
one
that
of
for the
those-
power as well, or only the ground?
Only the ground. Only the ground. I think I tried to do it for the power, but for some reason I decided to keep them separate.
Well, the only power we actually need is for the OLED display. Because, oh wait, no, that's not true. We also need power for the joystick. So we need, I guess, 3 power lines, one for each joystick and one for the display off of a single pin. So you'll have to have, like, I guess, like a smaller bridge maybe. Wow. Well, this seems like it's actually doable.
I think so. It looks very cool.
It just seems like this is such a better thing to use to fly around with, that if I want to take it somewhere, this is just...
If you remind me, I will bring you the LED ones, because anyway we can have them flashing on demand if something goes wrong, for example, battery low, for example, and it only flashes, well, it will kill you definitely the battery, so it's not a good idea, but...
Well, we have the OLED display for indicators.
It's true.
But, and we have the one LED that's built into the board. So if we want to try to, like, show something is happening when it's starting up, that it's blinking or something, if something goes wrong with the TinyGo program and it's not able to show any output of any sort.
Yeah.
That seems like it's probably enough, even though it sounds like it would look cool. Are they different colored LEDs or the same ones?
Yes, red, green, blue, and yellow.
Okay, I'm sold. Just because, like, these caps, they're like these caps these were really cool caps until you told me about the
They
LEDs.
are, but the LEDs.
Now the LEDs make these caps, they're not even nice anymore.
I think the footprint is a little bit bigger than that. I think it takes 3 of those rather than 2. So these are very, very tiny. That's another thing that maybe...
This is the smallest button I have that I can actually push. And we don't have room for a lot of the buttons. And so we really have, it's nice to have 4 buttons because you have takeoff, you have landing, and then you have 2 control buttons, which you can, for example, one of them can be the flip.
And they go home.
And then the other one could be like emergency landing or something. Or like in the case of my Bluetooth drone, I have the built-in pellet shooter that I've never used. So that way we could have like a trigger, as well as a flip. Because that way you could do a flip and then, or shoot them with the pellet thing and then do a flip to, celebrate your victory or something. Something like that. Well, maybe next week we can actually try to work on this a little bit. I think if we get the
I don't
Heathers,
have these ones. I'm sure 100% I don't have them, unfortunately.
Yeah, the only ones I have are
we
these.
This will be, I mean, we don't have to force wire wrap for everything. I mean, we can do the prototype maybe and then wire wrap whatever I don't know. Well, with the longer one, it will be much easier to. Well, I mean.
Well, if we just do what you were suggesting,
connectivity,
is this too short? By the way, is this too close together?
To wrap them or to solder? No, to wrap, I think it fits perfectly. There is no problem. The problem is then to pass the cable. Depends what you would like to do. It's not if you have to connect this one to this one as a short distance, you have to do some sort of bridge, so longer. Otherwise, you cannot.
Well, naturally, it doesn't work out that simply because this is where the SPI interface is, which goes to the display, not to the joystick. So actually, this is not the best location, is it?
Wire wrap is because you want to change the position and get to the right point, or is because otherwise we can solder it if we know the connectivity and the layout, let's say, and forget about it. But probably.
Well, the wire wrap is because
we can move it.
Well, first of all, it looks really cool.
It does.
And it takes up a very small amount of space. The thing about soldering the wires is the wire is going to be kind of loose if you have enough room to solder it, whereas the wire wrap, it's so cool because you just tighten it right up and it just makes everything so clean.
At the end, I ended up using some hybrid solution as usual, because only wire wrap, if there are some components like even the switch. Let me show those pins. No, this is okay. For example, the button I was mentioning has very short pins.
I see.
So using a mixture could be, at the end probably we'll end up having to solder something. It's not 100%, but let's say, for example, when you are working around the microcontroller where there are many pins, this is where it comes very useful. And for example, for the soldering, these kind of things, it's the best because you don't lose anything.
Because you see, we are using many of the pins. Like there's a bunch here that are not actually used, which are the SPI interface. So if I was going to use a better display, like a higher speed display, color display, then we'd need the SPI interface. So that might be a future upgrade.
Yes.
Because it's only a couple more pins. I may or may not have a color OLED SPI display, or a TFT rather. But it sounds like this would probably be, if what we're trying to do is this, but with another joystick, it sounds like just using a combination of soldering and wire wrapping would be the best plan.
Exactly. Because there are some connections that you know you're not going to change, but the ones you plan to change because you have to add or experiment or replace something, this is where it's very nice to have wire wrap rather than soldering. Especially because, I mean, to desolder this, it's, mission impossible.
Yeah, no, once it's soldered, it's forever.
I started using the sockets because at least I throw this one, but not the...
My hardest thing is getting it out of the socket without bending the pins.
Yeah.
Yeah, it's better to use like a chip puller, which I have one, but I never pull it out. I always just try to pull it out, and I usually end up bending one of the other pins. But if it's then you have to desolder obviously all of them to get it back on. That's the advantage of only doing this once with wire wrap, at least. All right, well, let me look at my collection of headers though, because if I have some of these that are longer, then that solves the whole problem.
There are some of these that are natively bent at 90 degrees.
I may have that as well. This is not my only bag of headers. I actually found my box of parts
I'll have
where I have like a whole box just full of headers and parts.
I know I have these ones bent at 90 degrees. I know I have them, but not sure about these ones.
I have the pins bent at 90 degrees that probably you gave me, but not the headers.
Okay.
Well, let me look to see what I've got, and then I'll bring them with me next week, and maybe we can actually try to work on it.
Okay.
Cool, man. Well, thank you very much.
Nice to see you again.
Yeah, thanks for coming. That's so awesome. Oh, man. I can't tell you how much I'm looking forward to that. Just because, you've seen me and my little foibles with these, breadboards, which are really fun, but it's time to take this controller to the next level. All right, so let's see, what did we do today? Talked about some news and the foibles of controlling remote vehicles in space from a ground station. Good luck up there, International Space Station peoples. We merged, actually we didn't actually merge any pull requests, we just did some serious review of the SPI additions to the RP2040. So hopefully SoyPat can make some of those changes and we can get them merged in really soon. And then took a look at the next generation flight control stick for the tiny flight controller, the upgraded version of what I was showing in my talk last week for the TinyGo hardware mini-conf. So that's it for today. Thank you everybody for hanging in there. Thank you so much for my technical staff for working on getting everything just dialed in. and we will see you next week. Farewell, humans.